Students, welcome to my video tutorial. This time, I'll be discussing questions on periodic motion, specifically simple harmonic motion. Question number 1. An object like that shown in the figure oscillates back and forth. Which entry or entries in the table correctly describes the displacement x? For each of the following values, the object's x velocity or v sub x and x acceleration or a sub x. We need one or more answers. So, uh, in the sketch, we have an object that is attached to a spring. One end of the spring is fixed to the wall, and if you're going to pull the object to the right, okay, that's going to make this spring stretch to a certain distance x, right? So, uh, there is a force, okay, known as the restoring force. If you are going to release the object, all right, so what happens is the object will oscillate, meaning it will vibrate to the right and to the left, or to the left then to the right, okay? And this kind of motion is what we call a periodic motion, okay? This is a kind of motion that repeats itself in a definite cycle. It occurs whenever an object has a stable equilibrium position, also known as the relax or rest position, and that there is a restoring force that acts when the object is displaced from equilibrium. Okay, so a special kind of periodic motion is what we call a simple harmonic motion. So this object can be considered in simple harmonic motion if the restoring force F exerted by the spring will obey what we call Hooke's law. Okay? Hooke's law states that the restoring force F is directly proportional to the change in length delta x, sometimes called the elongation of the spring. So when converted into an equation, we can have F is equal to negative k times delta x, where the constant k is called the force constant. The sign is negative because the restoring force is always opposite to the displacement of the body that is in simple harmonic motion. All right? The force F here is considered the net horizontal force, okay, when applied to our question number 1. Okay? Other forces such as force of gravity and the normal force are disregarded because anyway, when they are added vectorially, their sum is equal to 0. So we are only concerned with the net horizontal force acting on the system. All right. So our choices, you are to determine what is the correct sign of the displacement x, okay, for a given velocity dx as well as for a given acceleration x. For example, option A, if Vx is positive, meaning greater than 0, and then Ax is positive or greater than 0, then we will have a displacement that is less than 0 or a negative displacement. Okay. For option B, if Vx is positive and Ax is negative, then the displacement must be negative. For option C, if Vx is negative and the Ax is positive, then the displacement x must be positive. For option D, if both Vx and Ax are negative, then the displacement must be positive. For option E, if Vx is 0 and acceleration Ax is negative, the displacement x must be positive. And the last option, F, if Vx is positive and Ax is 0, then the displacement must be equal to 0. So, which among these can be considered a correct description for the displacement of the body x? Okay, we need one or more answers. So you just apply the concept, specifically the concept of simple harmonic motion, where the direction of the F-net and that of the displacement are always opposite. Since when there is a net force acting on the system, we say that the body is also accelerating. So the direction of the force must be the same as the direction of the acceleration. So it is based on this Hooke's law formula where we can describe the relationship between the acceleration and the displacement x. What do you think is or are the correct answers? All right, so our correct answers are, okay, first, we say that the displacement x and the acceleration ax should always have opposite signs. Okay, it doesn't matter what the direction of the velocity vx is. All right, so if we look at each of the options from A to E, all right, it looks like that in letter A, we have here, if Vx is positive, Ax is positive, then the displacement x is negative. All right? So, whatever is the direction of the Vx, if the Ax and the displacement are opposite, that means such relationship is true. All right? But if you look at option B, it says here, if Vx is positive, Ax is negative, then the displacement x is negative. That cannot be because Ax must be opposite in sign to the displacement x. Option C as well cannot be considered because Ax and displacement x are both positive. But option D can be considered correct because Ax is negative, then x must be positive. And likewise, if Vx is 0 uh, and Ax is negative, then the displacement x must be positive. Okay? Now, for a case where the acceleration is 0, all right? Acceleration being equal to 0 means that the speed or velocity is constant. All right. So at that point where the velocity is constant, is the displacement equal to 0? Okay. The answer is yes. Because at x equals 0, we say that the body as is located at its equilibrium position, also known as the relaxed position. So if F net, or the restoring force, is 0, all right, it follows that the acceleration is also 0, and that the body is located at x equals 0. So in other words, our correct answers are options A, D, E, and F. Question number 2. Spring is mounted horizontally with its left end fixed. A spring balance attached to the free end and pulled towards the right with a force of 6.0 Newton, causing a displacement of 0.30 meters. We replace the spring balance with a 0.50 kilogram glider. Pull it 0.020 meters to the right along a frictionless air track, and then release it from rest. Question. Find letter A, the force constant K of the spring. B, the angular frequency omega, the frequency small f, and the period capital T of the resulting oscillation. So as shown in our diagram, we have here the spring, all right, the spring with its left end fixed. It is mounted horizontally. The right end is connected or attached to a spring balance, okay, that registers how much force is being exerted on the spring. Like in this problem, a 6 Newton force, 6.0 Newton force causes the spring to have a displacement of 0.030 meters. All right, so value of x, okay, is 0.030 meters. Its original equilibrium position is labeled here as x equals 0. Okay, now, when the spring balance is replaced, okay, by a mass equal to 0.50 kilogram, which actually is a glider, all right, and the glider is, you're going to pull the glider to the right, okay, along a frictionless air track, okay, to a distance x equals 0.020 meters. So, as shown in sketch letter B, we are asked to find the force constant K of the spring, as well as the angular frequency omega, the frequency F, and the period of the resulting oscillation. So our solution for this problem, okay, will be shown in the next slide. All right, so here are the solution to this question. We first find the force constant K, and this is simply using Hooke's law formula. Okay, from Hooke's law formula, which we earlier presented, the force F, or the restoring force F, is equal to the negative of the force constant K multiplied by the change in displacement, or delta X. But since it's force constant K that we are after, so we just isolate the formula, and this becomes K is equal to negative F over delta X. Then when we substitute, all right, uh, the value of the force is negative 6 Newton, okay, and that of the delta X, or the displacement, is 0.030 meters. Hence, the force constant K, disregarding the negative sign, because force constant K is always positive, we have the value 200 newtons per meter. So that is the what we call force constant. When you are talking about a spring, sometimes it's also called the spring constant. So in the next question, where we now have a glider with a given mass of 0.50 kilogram attached to the right end of the spring, and then we pull the glider to the right, causing it to have a displacement equal to 0.020 meters. And then from rest, we release, all right? We release the glider, and since it is attached to the spring, naturally the glider will move, all right? Will move to the left because it is being pulled by the spring in the direction leftward, or to the left. Okay, what happens is the glider will overshoot, okay, the rest position and goes beyond, or uh, to a displacement that is considered negative, all right, or to the left of the rest position. And then somewhere to the left of the rest position, the glider will stop momentarily, okay, and then it will again move to the right and then overshoot again as it continues to move to the right. This happens because the air track produces no frictional force. And so, uh, without friction, the body will simply oscillate or vibrate left and right, left and right, like a simple harmonic motion. And that's exactly uh, what we are asked to determine. Okay, the problem letter B is asking us to determine the angular frequency denoted by omega, right? So this angular frequency omega can be determined using the formula square root of K divided by the mass m. We already know what the force constant K is, and the mass of the glider is given, so we just substitute. Okay, omega becomes, or is equal to, the square root of 200 kilogram per second squared. Okay, instead of Newton per meter, we can also express the force constant in terms of kilogram per second squared. That will be divided by the mass 0.50 kilogram. So with the help of your calculator, we can determine the value of the angular frequency omega, which is when expressed in radian per second. This is our answer. Omega is equal to 20 rad per second. Angular frequency here should not be confused, okay, with uh, the same symbol used in rotational motion. Okay, omega is also the symbol for what we call angular speed or angular velocity. Okay, but when you say angular frequency, that is different from what uh, is discussed in rotational kinematics. All right. So we now continue. Aside from omega, we also are required to determine the frequency f. All right. So frequency here is defined as the number of cycles. How many complete cycles or how many complete vibration does the body have, okay, per unit time. But in terms of the angular frequency, omega, we just, all right, divide angular frequency omega by 2 pi. That is how we get the frequency f. All right. Since we know already omega, 20 rods per second, we divide it by the value 2 pi. All right. And again, with the help of your calculator, we will get the frequency f equals 3.2 cycle per second. Okay, or that can also be read as 3.2 vibrations per second. Okay, which in SI system is the same as hertz. Cycle per second can also be expressed as hertz. In other words, our value for the frequency f is equal to 3.2 hertz. And lastly, for the period, capital T. By definition, when we say period, we are referring to the time it takes, okay, for a body in simple harmonic motion to have one complete cycle. The time elapsed, okay, for the body to make a complete cycle or vibration. And that incidentally is equal to the reciprocal of the frequency f. Alright, so the period t is just equal to 1 over f or 1 over 3.2 hertz. So getting the reciprocal of 3.2 hertz, our period is equal to 0.31 second. Question number 3. Suppose the glider in question number 2 is given an initial displacement x naught, which is equal to positive 0.015 meters, and an initial velocity v naught x equals positive 0.40 meters per second. Question letter A, find the period capital T, the amplitude capital A, and the phase angle phi of the resulting motion. Question letter B, write equations for the displacement, the velocity, and the acceleration as a function of time. Alright, so this sketch was already shown earlier when we were discussing question number 2. Alright, so our first question is for us to find the period t, but earlier we already got the value of the period, and that was equal to 0.31 second. So this was the value of the period, okay, for the same body, the glider, And then the angular frequency was also determined earlier as 20 rods per second. Okay, so we put it here again because we'll be needing this in order to determine the amplitude, capital A. All right. These two variables, by the way, uh, they don't depend on the amplitude. Okay, the amplitude of the resulting motion, because they are actually dependent on the value of k, the force constant, as well as on the value of the mass of the oscillating body. Right. So, how do we determine the amplitude, capital A? Using the formula, A is equal to the square root of x naught, all right, squared, plus uh, v naught x squared divided by omega squared. So, since we already know each of these quantities, we just substitute square root of for x naught 0.015 meter, then square it for v naught x, it is 0.40 meter per second. Okay, square that, and then all over or divided by the square of the omega, the angular frequency, or omega, 20 rad per second. Okay, so doing your math, we will get, okay, the value for the amplitude, which is expressed, or which is equal to 0.025 meters. Okay, the amplitude, by the way, is referring to the maximum displacement that is acquired by the oscillating body. Okay, uh, the one to the right of this equilibrium position, okay, where the value of x is positive, and if that happens to be the maximum displacement, then we say that that is the amplitude. Likewise, to the left of the equilibrium position, we also have a negative maximum displacement. But the magnitude of that negative displacement is known also as the amplitude. So it is always expressed in positive number. That's for the amplitude. What about for the phase angle phi? Okay, the phase angle phi can be computed using the formula arctan of the ratio negative b naught x divided by omega times x naught. Take note there is a negative, okay, for the v naught x. So substituting again, b naught x, omega and x naught are all given. So using your cycle, we will get as our phase angle P in degrees, it is equal to negative 53 degrees. But phase angle is usually expressed in radian. So our answer is negative 0.93 rad. So that's our answer for letter A. Now for letter B, we are asked to write equations for the displacement, velocity, and acceleration as a function of time. Alright, so for the displacement, okay, we have this formula, a general formula. X is equal to the amplitude multiplied by cosine of the quantity omega t plus the phase angle phi. Alright, so we know what the amplitude is, what the omega, and the phase angle phi. So we just write them, okay, as a function of time t, of course. And that becomes our displacement x, okay, can be determined at any given time as 0.025 meters multiplied by the cosine of 20 rad per second, okay, multiplied by the time t, then minus the cosine of 0.93 rad. This is our formula or equation for determining the x displacement, okay, at any given value of time t. Now, for the velocity equation, we use this general formula. Vx is equal to the negative omega times the amplitude A, okay, multiplied by the sine quantity omega t plus the phase angle phi. And then again, in terms of the time t, since we know omega, we know capital A, and we know angle P, we just substitute, okay? There's a negative sign here, 0.50 meter per second, multiply that by sine of the product of omega times t, or 20 rad per second times t, minus, okay, the sine of 0.93 rad. This is our phase angle. So that is our equation for determining the value of the velocity at horizontal velocity vs at any given time t. And finally, for acceleration, the equation for acceleration ax is equal to the negative of omega squared multiplied by the amplitude and the cosine of omega t plus the angle p, okay, quantity, omega t plus angle p. And substituting again, we have negative 10 meters per second squared will be the result of multiplying the omega squared and the amplitude. Okay, you can check that out. I leave that to you, how we got 10 meters per second squared. And then multiply that by the cosine of 20 rad per second multiplied by any value of time t minus the cosine of the phase angle 0.93 rad. So these are the needed equations in finding the displacement x at any given time, in finding the horizontal velocity at any given time t, and finding the acceleration ax at any given time t. Before we proceed to our next question, let's first uh, clarify what we mean by phase angle. All right. So the constant, the Greek letter phi, represents what we call the phase angle. This phase angle tells us at what point in the cycle the motion was at time equals 0. We denote the displacement at time equals 0 by x naught. So x naught can be expressed as a cosine of angle phi. If, for example, angle phi or the phase angle is 0, then our equation for x naught becomes a cosine 0. But cosine 0 is equal to 1, and that means our x naught is just equal to the amplitude a. And that is similar to what is shown in the graph, the one colored green. Alright? So this green curve represents a phase angle equal to phi that is 0. Alright? This is a graph that shows the relationship between the displacement x and the time t. We have three different variations of simple harmonic motion. They all have the same mass m, the same force constant k, and the same amplitude, capital A, but different phase angles, phi. Alright? So this is how the graph look like if we start at angle phi equals 0. If the phase angle is equal to 0, then that's how the graph looks like, the one in green, right? If, for example, the angle, phase angle P is equal to pi, all right? From 0, for example, uh, pi radian, then our value for x naught will simply be a cosine of the angle P. Okay, cosine P is just equal to the negative of negative 1, which means that our x naught is equal to the maximum negative displacement, or negative a. That actually would be a graph. For example, uh, one half of the period, okay, after, this is how the graph would look like, okay, from t over 2, there you go. But if that is at time 0, then it will be somewhere here. So we will have a graph similar to the continuation of the graph curve colored green, something like that. But starting at negative a, right? So the pink one pertains to a phase angle that is pi over 4, while the yellow one, or the golden curve, represents a phi, or angle P, equal to pi over 2. Okay? This is how a phase angle at pi over 2 look like. Question number 4. A glider is attached to a spring as shown here. If the glider is moved to x equals 0.10 meter and then released from rest at time t equals 0, it will oscillate with an amplitude capital A equals 0.10 meters and the phase angle phi equals 0. Now, question letter A. Suppose instead that at time 0, the glider is at x equals 0.10 meter and is moving to the right. Okay, so in this situation, is the amplitude greater, less than, or equal to 0.10 meters? Is the phase angle positive, negative, or is it equal to 0? That's for letter A. Now, question letter B. Suppose instead that at time 0, the glider is at x equal to 0.10 meters and is now moving to the left. We just reverse the situation in letter A. Okay? So in this situation, letter B, again, the question is the amplitude positive, negative, or is it greater, less than, or equal to 0.10 meters? And is the phase angle positive, negative, or is it equal to 0? So, we, of course, answer letter A, but the answers for both questions A and B are actually this one. Okay? For A, for the amplitude, question letter A, the amplitude will be greater than 0.10 meter and the phase angle will be negative or less than 0. While for question letter B, the amplitude will still be greater than 0.10 meter, but the phase angle is greater than 0. Explanation. At time 0, in both situation A and situation B, the initial velocity or v naught x is non-zero. Okay? B naught x is non-zero. So therefore, in our equation for the amplitude, which is square root of x naught squared plus v naught x squared divided by omega squared, it's obvious that if v naught x is not zero, then obviously the resulting amplitude, okay, which is square root of x naught squared plus there is a certain additional plus base of not x, since it's not zero, eventually we will get a value for the amplitude that is greater than x naught. Alright, so that is our first analysis for both cases A and B. Now, what about the phase angle? For the phase angle phi, we have the formula angle P is equal to arctan of the ratio negative b naught x divided by omega x naught. Alright, so if the angle phi or phase angle phi is positive, okay, that is simply because the ratio negative b naught x over omega x naught is also positive. Alright, and if angle phi or the phase angle is to be negative, then it's because the ratio negative b naught x over the omega x naught is negative. So that explains why in letter A, the phase angle is negative or less than 0, while in situation B, the phase angle is positive or greater than 0. This is now the last question, number 5. Consider the problem in question 2 where the force constant K is equal to 200 Newton per meter and the mass m is equal to 0.50 kilogram and the amplitude is equal to 0.020 meters. Now, questions. Find, letter A, the maximum and minimum velocities attained by the oscillating glider. Letter B, the maximum and minimum accelerations. Letter C, the velocity Vx and the acceleration Ax when the glider is halfway from its initial position to the equilibrium position x equals 0. And question letter D, find the total mechanical energy, the potential energy, and the kinetic energy at this position. So, the concept for this last question is just the conservation of mechanical energy, the law of conservation of mechanical energy applied to simple harmonic motion, which says that the total energy E is equal to the sum of the kinetic energy or 1/2 mvx squared plus okay, uh, the elastic potential energy 1/2 kx squared. And this can be also expressed in terms of okay, 1/2 k multiplied by the square of the amplitude. So this amount of mechanical energy is always constant at any position, okay, in the cycle. So we will now calculate first for letter A, the maximum and minimum velocity. So to find the value of the velocity, Vx, okay, we use the formula plus minus square root of k divided by the mass m multiplied by the square root of the amplitude squared minus the displacement x squared. So we have two radical symbols here. Okay, and the sign for our Vx could either be positive or negative. The Vmax, all right, the Vmax is expressed as positive or negative square root of k divided by the mass, then multiplied by A. So the A here is the maximum, represents the maximum displacement. That's why from our general equation to find Vx, it can be reduced to this form if what we are talking about is the Vmax, because uh, the velocity of an oscillating body in simple harmonic motion is said to be maximum when x is equal to 0, meaning at the equilibrium position. So, from this general formula, if x is equal to 0, then we will just have square root of a squared, which is, of course, equal to a. So our formula has been reduced to positive negative square root of k over m multiplied by a. Okay, the a is not inside the radical sign. It is outside. All right? So we can now substitute the value of, or square root of, the value of k, which is given in the problem, 200 Newton per meter, and they divide that by the mass, 0.50 kilogram. Get the square root. After getting the square root, okay, that will be multiplied to 0.020 meter, which is the amplitude. And then, after multiplying that to the square root of this two numbers here multiplied or divided by, we will get the Vmax equals 0.40 meters per second. All right, so this is the maximum velocity. We choose the positive because when you say maximum, we actually mean the positive velocity greater than 0. All right, that's why it is positive. And for the minimum, what is the minimum velocity? All right, because the question is asking also for the maximum and the minimum velocity. So for the minimum velocity, we just put a negative sign. All right. Remember, our general formula suggests that we're expecting either a positive and a negative value for Vx. So if the maximum V is 0.40 meter per second, then it follows that the minimum is negative 0.40 meters per second. So moving on to letter B, what is the maximum and minimum acceleration? Okay, So the formula for finding the acceleration ax is just equal to negative quantity k over m multiplied by the displacement x. All right? And maximum acceleration happens when uh, the value of x is equal to the amplitude. All right? So that maximum acceleration happens, okay, if our amplitude is that of a negative displacement x. So we will have a double negative. When we substitute, we have negative 200 Newton per meter divided by 0.50 kilogram and then multiplied by negative of the amplitude, which is 0.020 meters. Okay, and what we will get is a positive value for acceleration, and this is considered the maximum acceleration, while the minimum acceleration, of course, is negative 8.0 meter per second squared. These are the answers for letter B. Okay, so for our solution to letter C and to letter D, they will be presented in the next slide. For question letter C, okay, the point halfway from x equals x naught or the amplitude A to x equals 0 is of course equal to x equals A over 2, which is 0.010 meters. So using that value for our x, we just substitute in the formula, finding the Vx, all right, which is equal to negative square root of k over m multiplied by square root of a squared minus x squared. All right, so substituting, okay, negative square root of 200 newtons over Newton per meter divided by 0.50 kilogram, okay, get the square root of that, and then multiply to the square root of uh, the amplitude square, that is 0.020 meter squared minus, okay, the square of the value of x, which is 0.0110 meter, square it, all right? So simplifying, we will get for the Vx as equal to negative 0.35 meters per second. Okay. Um, the negative sign here, which is the result of simplifying what we have here, okay, uh, it implies that the glider is in fact moving from the maximum displacement x, which is equal to a, okay, towards the value of x is equal to 0. In other words, the glider is moving to the left, okay, approaching the equilibrium position from the maximum position x equals a, hence the negative sign of the velocity. Now, for our last question, letter D, energies. First, we'll calculate for the total mechanical energy using the formula 1/2 k a squared. All right, so substituting 1/2 times 200 Newton per meter multiplied by the square of the amplitude, 0.020 meters, square it, and then multiply that and divide by 2, we will get as the total mechanical energy equals 0.040 joules. Now, for the elastic potential energy, which is U, equals 1 half kx squared. Substituting, we have 1 half multiplied by k, or 200 Newton per meter, multiplied by the square of the displacement x, or 0.010 meters squared. Simplifying, we will get the elastic potential energy equal to 0.010 joules. And finally, for the kinetic energy, which is 1 half mv squared or vx squared, substituting 1 half multiplied by the mass, 0.50 kilogram, and the square of vx, all right, the vx that we obtained earlier in letter C, square of 0 or negative 0.35 meter per second, okay, simplifying, our value for the kinetic energy is equal to 0.030 joules. Okay, and if we add this amount of kinetic energy plus the amount of elastic potential energy, okay, of course, we will get the total amount of the mechanical energy, 0.030 joules plus 0.010 joules, of course, is equal to 0.040 joules. Okay, which shows that the law of conservation of mechanical energy, okay, has been applied in this problem. So that's about all. Thank you very much.